All right, number 79 and 83 are both proofs. Not like geometry proofs, but proofs nonetheless. Basically, given any complex number z that has the form a plus bi, this is kind of a general way to say any complex number, they're asking us to prove this statement. And I think just understanding what this statement even says is the first step. This says, remember, z bar is the conjugate. That's a minus bi, the complex conjugate. This says, if you take the conjugate of z and then square it, does it give you the same answer as if you take z, square it, and then take the conjugate? It's kind of a order of operations type of thing, I guess. So we're supposed to prove that it doesn't matter if you take the conjugate first and square it, or if you square it and then take the conjugate. So to prove this, I'm going to start with one side, and I'm just going to work it until I get the other side. And I don't think it really matters on this one which side I start with. I guess I'll start with the left-hand side. So here's my proof. I'll start with the left-hand side. I'm going to take the conjugate of z, and then I'm going to square it. So substitute in z. Z is a plus bi, conjugate, squared. So this bar over top of it says take the conjugate of that number on the inside. Conjugate, that would be a minus bi, the complex conjugate. Now I need to square that. Square the first, I get a. Multiply these together and double it, I get negative 2abi. And then square that, you get plus b squared I squared. Don't touch the screen. I'm working here, honey. My 11-month-old is trying to help. Okay. I squared is a negative, so that makes that negative. So the real component is, Cece, come on now. The real component is a squared minus b squared. And then the imaginary component is negative 2. No, honey. Cece, stop it. Stop, honey. Okay, yes. Negative 2abi. So this is the real component, and this is the imaginary component. So the trick then is to show that this is equal to the other thing. Now, it's going to be hard for me to work this and show you that it's the same as the other side. So I think what I'm going to do is I'm going to now work from the right-hand side, excuse me. And I'm going to show that when I do the right-hand side, it gives me the same thing as this. Okay? Right-hand side is z squared and then take the conjugate of it. So this says, first of all, z is a plus bi. So here, the first thing I'm supposed to do is square it and then take the conjugate, as opposed to taking the conjugate and squaring it. So this becomes a squared plus 2abi plus b squared I squared. Now I got to take the conjugate of that. So first, let's separate the real and the imaginary. So this is negative. So this gives me the real component of a squared minus b squared plus 2abi. And I have to take the conjugate of that. So to take the conjugate of this, the complex conjugate, we're going to take the real component, and then we're going to take the subtract the imaginary component. So that is a squared minus b squared minus 2bi. So as you can see, since the left-hand side is equal to this, and the right-hand side simplifies to this, and these two simplify to each other, then, by the transitive property, I know the left-hand side is equal to the right-hand side. Kind of a little bit of a cheater way to do it, but it's all right. Okay? That's good enough.